Hello everybody. We are very happy to have Adam Pound with us today. So Adam is a Royal Society University Research Fellow and a permanent member of staff in the School of Mathematical Sciences at the University of Southampton. His research focuses on classical general relativity and gravitational wave science, where he has contributed to the theoretical understanding of relativistic motion and binary mechanics. He's a member of the LISA consortium, where he heads the consortium's effort to develop theoretical models of extreme mass ratio in spirals. And today he's going to tell us all about that. Take it away, Adam.
Thank you. And thanks for the invitation to give this talk. It's an unusual opportunity to talk to a fairly broad audience. As I was saying a few minutes ago, I might have pitched this even a bit too broadly, but we'll see how it goes. Okay, so the main subject here is gravitational wave astronomy, but I'm going to be focusing on a particular aspect of it, which is compact binaries, so the two-body problem, in a very particular regime where one body is much smaller than the other one. So I'll cover three topics. One is just an introduction to gravitational wave astronomy, where it currently stands, where it's going, and introduce you to these particular kinds of binaries called extreme mass ratio in spirals, where again, one of the objects is much smaller than the other one in the binary. Then I will talk about how we model these systems. So EMRI stands for extreme mass ratio in spiral. And I'll connect it up to something you might not often hear talked about in the context of gravitational wave astronomy, which is the equivalence principle. So we get a kind of very specific, precise look at the equivalence principle from these systems. Then at the end, I will briefly discuss the current status of EMRI models and what I've been working on a lot over the last 8 or 9 years, and a kind of surprising outcome that we have, which is that when formulated in a particular way, the Einstein equations are much less nonlinear than you might guess they would be. Okay, so let's start with just gravitational wave astronomy. So I think everyone in the audience will be aware of this. This was the beginning of gravitational wave astronomy now 6 years ago, almost 6 years ago, when LIGO detected gravitational waves from a black hole binary merger. So here's a picture you've probably all seen in some form. You have two black holes inspiraling as they emit gravitational waves. They get closer and closer, they merge, they form a single black hole that rings down into a stationary Kerr black hole. And this is the actual data from the detector. And there's the prediction from some combination of numerical relativity or effective one-body theory. But this is the theoretical prediction in black and the data in blue. So that was a huge breakthrough. That was a major milestone, and it got a Nobel Prize. Since then, these things have become very, very common. We detect them very, very frequently. I think here I'm only showing detections from the first 2 science runs. In the 3rd science run, LIGO and Virgo were actually detecting waveforms roughly once a week. So we now see these black holes all the time, and some of these also involve neutron stars. One more, there we go. Okay, so although we see a lot of signals, and there's some variety in the sense that some of them are neutron stars rather than just black holes, they have a pretty typical form that they all share, which we can see in this video. So this is 2 black holes orbiting around each other. They're roughly equal sized. One of them is maybe twice as big as the other one here. And the orbit is very, very circular. So although there's a lot of complicated physics going on, it's relatively simple as far as these things go. Everything's almost exactly circular, and the 2 bodies are very close to each other in size. Now, that's all going to change pretty soon over the next 10 to 15 years. So right now we have 4 detectors in operation, not at this moment, but once they resume their science run. So we have the 2 LIGO detectors, we have Virgo. Geo does continue to run, I think, but it never actually detects anything, and they never expected it to. Kegra did join the 3rd science run, but its sensitivity is not yet high enough to actually make any detections. But they are improving it pretty rapidly, so over the next few years, it should be making detections along with LIGO and Virgo. And LIGO India, before the pandemic, had an extremely ambitious schedule. I think they wanted to have it in operation by 2024 or something like that, but sometime relatively soon. So these will all be in operation. Then we'll have next generation detectors, the Cosmic Telescope, the Cosmic Explorer, and the Einstein Telescope, along with pretty major upgrades of LIGO. So these are going to see many more things than what we can currently see, and we'll have an even bigger expansion of what we can see when we have telescopes up in space. So this is the LISA space antenna, which is now a European Space Agency project with some involvement of NASA. And there's also this proposal for the Japanese detector, DeSaigo, which will detect different things than either LISA or ground-based detectors. And China also has, I think, 2 separate space-based detectors that are competing with each other right now for which one's going to get funded. But assuming everything goes well with LISA, at least one of those should get funded in China. So once we have this big detector array on Earth and in space, we're going to see a lot of different things that we can't currently see with LIGO and Virgo. So here's a quick sketch of the parameter space of binaries. So even once we have all these detectors up, still the main source of gravitational wave signals will be from binaries. But we'll just see more of the binary parameter space. So the main axes here are the orbital separation, how far apart are the 2 objects from each other, and the mass ratio. And then in different regions of the parameter space, you have to use different modeling methods. So down here in the corner, this is the region where LIGO detections reside. This is where the 2 objects are roughly the same size and they're very close together. And everything there is really dependent on numerical relativity, where you fully solve the fully nonlinear Einstein field equations. And then you have a bunch of approximations to that that you can use to more rapidly generate waveform templates. But then in different regions, you'll have different methods. Up here, where the objects are very far apart, you have post-Newtonian theory, which is a weak field, slow motion approximation. So this is when the mutual gravity between the 2 objects is very weak, and the objects are moving slowly. And so then gravity is almost Newtonian, and then you look at corrections coming from the Einstein field equations. Now, what I'm mostly going to be focusing on is down here in this corner, where one of the objects is much, much smaller than the other one. And so here I use a particular kind of perturbation theory called self-force theory that I'll discuss a bit more later. But the point is that already now, LIGO is starting to see somewhat of a broader range of signals. So they have seen a signal with a mass ratio of 1 to 10, where one object was 10 times bigger than the other. And so that is moving us out towards this end. And as we get space-based detectors and as the noise curve gets pushed lower to lower frequencies for the ground-based detectors, we'll also see more of this range up here, where the bodies are more widely separated. And so we're going to see more and more of this parameter space, which means we need much greater accuracy, and we need a wider variety of models. And so the models that are really hyper-focused on this regime down here, and not just this regime where the mass ratio is almost 1-to-1 and the separation is small, but also things are quite circular. The motion is very circular. So we're going to be seeing a lot wider variety of things. And so the next big push over the next 10 years is preparing for what we're going to see. So in order to extract any information from a gravitational wave, we need an accurate model that tells us, first off, if we've seen a wave, it tells us what created that wave. But also we need accurate models even to find the waves in the noise, because the waves tend to be buried inside the noise, and you need to do some kind of matched filtering in order to extract a signal using a theoretical template. So all of this really depends on having theory ready in advance. Okay, so I'm going to be focusing on this region down here. And these kinds of systems where one object is much, much smaller than the other one, they occur at the centers of galaxies and galactic nuclei. So this is images from the center of our galaxy around Sagittarius A star, the supermassive black hole that's, we presume, is hidden in there. And we think these objects, these stars, are orbiting around that black hole. So these images were created by the European Southern Observatory. So this image tells you that seemingly there's a lot of stuff going on in the neighborhood of this big black hole. But this will tell you kind of the scales we're looking at. So this star here was looping around in a relativistic orbit, but fairly mildly relativistic as far as things go. And the closest it gets to the black hole, or the closest any of these stars are known to get to the black hole, are a few hundred Schwarzschild radii, so a few hundred times the size of the black hole itself. Whereas these systems that I'm going to be talking about, these extreme mass ratio inspirals, they occur really, really close to these massive black holes. We don't expect to be lucky enough to get a signal from an orbit around our own massive black hole, Sagittarius A star. But it'll be a similar kind of galactic core in different galaxies. And you see, this is very much not a Newtonian orbit. It's not very much even a relativistic circular orbit. These are very tight, highly relativistic, highly intricate orbits. And we expect these to be mostly one small stellar mass object, a black hole probably, orbiting around a massive black hole that's maybe 1 million times as big as our sun. So that's comparable to Sagittarius A star. So we're expecting a stellar mass black hole orbiting something that's 10 to the 5 or 10 to the 6 times bigger. And what's really interesting about these sources is that even though it's so close, it takes a long time for this companion to fall into the big black hole. So we expect to get about 10 to the 4 or 10 to the 5 orbits, meaning 10 to the 4 or 10 to the 5 gravitational wave cycles within the LISA band. So these signals are going to be detected by the space-based detector LISA. And in that time, in those 10 to the 4 or 10 to the 5 orbits, almost all of them are within 10 Schwarzschild radii of the black hole. So this is a much, much, much tighter orbit than the kinds of things we're seeing these stars execute. So because of that, the smaller companion serves as an incredibly high precision probe of the black hole geometry. So here's a video just that we can contrast with the one I showed you earlier. So before we saw two roughly equal-sized objects going around in almost exactly circular motion, but slowly spiraling in. Now this motion, as you see, is much more complicated. Now it looks like the black hole is getting bigger and bigger. That's the camera zooming in. The black hole is the same size the whole way through. And there you go. So these are totally different signals and totally different systems than what we're used to with LIGO. This animation was created not with a high precision model. It was created with kind of a crude approximation, but the structure that you see will be true even in the real system, even with the fully accurate model that we hope to have ready by the time that Lisa flies. Okay, so this is just a quick rundown of a few of the things that we hope to get out of observing EMRIs. So we expect to get fundamental physics. We expect to get astrophysics.
Adam?
Yes.
So can I ask a question?
Yep.
The estimate of 10 to the 4, 10 to the 5 orbits within the Lisa band for an EMRI around a supermassive black hole, is that for a supermassive black hole around the mass of Sagittarius star, for example, or heavy? I mean, it should depend also on the mass of the central black hole, right?
It will, yeah. So the main signals we expect to see, just because of the frequency band that Lisa is sensitive to, would be what an astronomer would call a massive black hole rather than a supermassive black hole. So 10 to the 5, 10 to the 6 solar masses.
Thanks.
But
right,
number of
because
orbits, go ahead.
Yeah, for M87, I mean, this is a very, very long time, for example, like 10 to the 4, 10 to the 5 orbits. For a black hole that can be like 1,000 times more massive than Sagittarius star.
Yeah, so we don't expect to see EMRIs around something that massive, just because, again, because of the frequency band that Lisa is sensitive to.
Right. Right. Okay. Thank you.
But I should say that by the time it enters the Lisa frequency band, this thing will have already executed a huge number of orbits just to get there. So yeah, a lot of dynamics will actually already have missed by the time it enters into the Lisa band. But the stuff we've missed is weaker field, so somewhat less interesting. Okay, so fundamental physics. The thing I want to really focus on here is that in general relativity, every isolated stationary black hole is described by the Kerr metric. There's a unique metric that only has two free parameters, the mass and the spin of the black hole. And this is something pretty remarkable about GR, that every isolated stationary black hole is described by the same metric with only two parameters. Now, because of that simplicity in GR, and because EMRIs are offering this very precise probe of the space-time geometry around the black hole, we'll be able to very, very precisely measure whether the central object in the galactic core really is a black hole, and whether it really is described by the Kerr metric of GR. So people talk about the possibility that these things we expect to be black holes could be something else masquerading as black holes, some other exotic object that just looks dark as far as we can see it. So we'll really be able to test very precisely whether it really is a black hole, but also whether it's well described by GR. Similarly, you can also measure things about is there a real event horizon, or is there some amount of reflection off the surface? You can look for other kinds of deviations from GR, different wave polarizations, different strong field dynamics, and there's a long litany of other things you can look at. And because we have such a long signal with so many wave cycles, with such a rich structure, we expect that constraints on deviations from GR are going to be one or more orders of magnitude better than with any other currently planned experiment. So we're going to get really incredibly precise information out of these if everything goes well. Then we also get astrophysical information. So we get information about the stellar environment around these massive black holes. We can constrain the mass function of black holes, telling us how many black holes we have for a given mass in the universe. And we might even get some cosmological information. So there's the possibility of measuring the Hubble constant to around 1%. So that's not going to be competitive with the most precise measurements of the Hubble constant by the time LISA flies, but it will be a complementary measurement.
Can I quickly ask? So
Yeah.
for the astrophysics and cosmology, it's pretty clear what you mean, but what exactly is the test of the Kerr metric? What feature do you go for? And how
There's
do you
actually
know?
quite a few. So the main one is we can measure the multipole moments of the spacetime. And for a Kerr black hole, the quadrupole moment, for example, is uniquely specified by the mass and the spin of the black hole. And we can measure the mass and the spin and the quadrupole moment all to high precision. So we can test whether the quadrupole is given by the formula it would have if it's a Kerr black hole.
And quadrupole because it's the easiest to see. I mean, in principle, you can keep going higher, but
Yeah, it's the higher ones, the precision will not be as good. But yeah, you have, if you make even very small changes, because the waveform is so sensitive, the very small change will have a big impact that we can measure. So even things like if you have a tiny bit of reflection, so you don't have a real event horizon, even if it's the tiniest reflection coming from, you know, a Planck length outside of the event horizon, we would actually be sensitive enough to test it, to see if it's whether it's a real event horizon or not. Okay, so the one I want to focus on is.
But if I could just ask, one sometimes hears the statement that there's no experimental confirmation, observational confirmation of the Kerr metric. How would you respond to that?
Currently, I would say that's probably true. We have very compelling evidence that there's black holes, and we have compelling evidence that any isolated black hole should be a Kerr black hole.
But that's theoretical, right?
That's purely theoretical, yeah. So things, I mean, probably the thing that's come closest has been the Event Horizon Telescope, but that has not actually really been able to say that it's a Kerr metric. There's the possibility of a next generation, very long, what's it called? Very large, very long baseline interferometer, similar to the Event Horizon Telescope, that would be able to tell whether it's a Kerr metric, but currently it can't really.
Wait, okay, a very simple, basic question. I'm very ignorant about this, but how do you measure the multiple moments since we're at a fixed direction from the black hole?
So you can just put in by hand a deviation of the multipole moment from Kerr and measure its impact on the waveform. So what you would do is you'd have one model that has the Kerr metric, you'd have one model that slightly deviates from the Kerr metric, and you'd see.
Okay, you're not directly measuring the multiple moments. You're just looking at how, assuming the multiple moment, how it would impact the waveform that you measure.
So everything is inferred from the waveform. Everything that we currently measure is inferred from the waveform. The masses of the black holes that we measure, everything comes from the waveform. So it's an indirect inference.
Yeah, I'm only asking because it's not, I mean, is it the case that you could always say that the quadrupole moment that you get is compatible with a different black hole of a different mass and spin? So in other words,
you would optimize over all the different parameters. So you'd find what fits best And if it's possible to get an equally good fit with a different mass and spin and a different quadrupole moment, then you would say you haven't made a good measurement of the quadrupole moment.
And what's the forecasted precision for these tests? Say with Lisa.
For EMRIs, we expect to measure the mass and spin to about 5 significant digits. The quadrupole moment to, I think, about 3 significant digits, maybe.
Thank you.
So that's yeah, that's pretty dramatically more precision than we have with current LIGO measurements of masses, for example.
Let me
Okay.
can chime in here.
Yeah.
Salvo. You said the LIGO, and I showed up as a LIGO member. I guess, can you say something about waveform systematics though? Because I mean, I've done work on test of GR, and I know that it's very hard, especially if you find a violation, to make a strong case that excludes all other possible sources. Because as you said, what you're testing is just, does what's in the data agree with my model? But there may be other reasons why it disagrees, which are not violation of GR.
Yeah, so the data analysis problem is going to be incredibly difficult. The modeling problem is also incredibly difficult, even within GR, and then we're going to have to add other possible effects. So the good thing about EMRI waveforms is that because they're so sensitive, they tend to respond in quite distinct ways to different effects. So you usually can disentangle different effects from each other.
Oh, all right. Maybe after the talk, if you can put on the chat some references for this, I would love to read them.
Sure.
I
So I
don't
think
follow the list.
I think it's
Bye-bye.
very much still an open problem.
Okay, and the reason I ask is because you gave explicit numbers for the statistical uncertainty that you can forecast. So I was wondering whether they were similarly
yeah, okay,
stronger
yeah,
forecast for the systematic uncertainty from waveforms, say.
Let me make a note to give you that after the talk.
Thank you, appreciate it.
Okay. Okay, so, way over time already. Is that right? Okay. Right. So this is the main thing that I want you to get out of the talk. From this perspective, that these systems are very precise probes of black hole geometry. So the real reason here is that this is a very, very, as I said, extreme limit of the two-body problem, where it's almost a stationary Kerr black hole at the center. And also the secondary companion here is almost a test mass moving in the geometry of the big black hole. So because of that, we can observe very tiny deviations from the Kerr geometry. And we can also observe very tiny corrections to geodesic motion. So I've discussed this first one a bit. Now, I think I'm going to talk about this next one in the next section. So how do we actually model these things? And how is it related to geodesic motion and to the equivalence principle? And this thing I'll call the generalized equivalence principle. Okay, so we model these things using gravitational self-force theory. I'm not going to get into any of the technical details, but the basic idea is you got a small mass, you got a big mass, you take your metric that describes the system, the binary system, and you write it as a series expansion in powers of this small mass ratio. So this is a small parameter in your system. And then you're just doing perturbation theory. So the leading order term, the 0th order term, is the metric of the central object if it were isolated. So that's going to be the Kerr metric. And then we have perturbations due to the small companion. And the small companion can be a black hole or a neutron star or possibly a white dwarf, but it's mostly focused on black holes. Okay, then these little perturbations, they actually affect the motion of the companion. So if we write down a covariant equation of motion, this is a covariant acceleration. If we were moving on a geodesic of the Kerr metric, we would have identically 0 on the right-hand side. But instead we have small corrections due to these perturbations. And so we say that the perturbations exert a self-force on the companion. Now, to link that up to the equivalence principle, let me go to the kind of things we normally tell undergraduates or in public lectures. This rubber sheet analogy. So we say, okay, we put a heavy object on this rubber sheet, it deforms space-time, and then an orbiting object is really just moving around as you would expect an object to move on this sheet. So the physics there is that this thing's a test mass, and it's moving on a geodesic of the deformed space-time. So another way of saying this is this statement of the equivalence principle. The equivalence principle means a whole bunch of different things to different people. But here I really want to specifically connect it to geodesics. So the statement is that a freely falling observer measures the same thing that an observer moving at constant velocity in flat spacetime would. So say this guy falls in, and then he meets this object that's orbiting around. Then, see if I can get the zoom in. There we go. And in this local little patch, everything looks flat. This guy's following a straight line, which is an approximation where it's what a geodesic looks like locally in this little patch. And the orbiting body is also moving on a straight line, which is again what a geodesic looks like in a local patch. So the idea is zoom in on a region. Everything's moving on a geodesic because locally it looks like flat spacetime, and in flat spacetime, everything moves on straight lines, or test bodies move on straight lines. Okay, but this is really just an approximation, this equivalence principle. It's really talking about a test particle. So it's something that is a test body in the sense that it's not gravitating, so it doesn't influence the gravitational field around it, but it's also very small. So the idea is it's a limiting statement that if you make the mass of the object small enough and the size small enough, then no matter what the object is, it's going to move on a geodesic to leading approximation. But it is just an approximation because this thing is going to deform the space-time. So here's something more like our EMRI, where you'll have a black hole here that has an infinite throat, and you have something orbiting around, and the little thing is going to deform the space-time. And that's going to correct the geodesic motion. So you're not going to have geodesic motion, you're going to have small corrections to it. And even if it weren't gravitating, if it has a finite size or a finite spin, that also causes deviations from geodesic motion, even if it's a test body that's not gravitating. So in these systems, these EMRIs, where we have a small thing going around a big thing, we're really measuring very tiny corrections to the geodesic equation. So how do we figure out what those corrections are? The basic mathematical method is this method of matched asymptotic expansions. So here's our binary system. The idea is we zoom in on a region around your little object, and there we can identify different regions of interest. So out here in the external universe, that's significantly far away from the small object, you can treat the metric as approximately the metric of the big black hole, plus small corrections from the small body. But then if you get close enough, the small body is actually going to be dominating the gravity. It's going to have a much stronger effect on the local tidal fields, for example, than the big black hole has. So you design a different approximation that zooms in on this region, where the small body is your leading approximation, or the spacetime of the small body is your leading approximation, rather than the spacetime of the big body. And then you feed information back and forth in a particular mathematical way. So what comes out of this is when we solve the Einstein equations, everything comes from the Einstein equations. When we solve the Einstein equations outside of the little body, we get this nice split of the full metric into different pieces. So this is now not a rubber sheet. This is space-time with time running up and to the right. And this little blob here is your small body. So this is the full metric of the system. And the idea is you can split this into a self field that's dominated by the local gravity of the small body, and then an effective metric, which is your background metric of the big black hole, plus a particular piece of that perturbation that was due to the small body. And this does not look like it's, part of the body's gravitational field. It's just kind of slowly varying in the neighborhood of the small body. So this self field is directly determined by the object's multipole moments. So this is a small object. It has a mass, a spin, quadrupole moment, and higher moments. But then this effective metric doesn't directly involve those multipole moments. It's instead a smooth vacuum metric that's determined by global boundary conditions far away. And then the key kind of foundational result from self-force theory is that you find the Einstein field equations dictate that your small object does move as a test body, but not a test body in the metric of the big black hole, instead as a test body in this effective metric that includes part of the perturbation created by the small body itself. So we call this an equivalence principle because this doesn't depend on details of the body, but it's a generalized equivalence principle. It's saying that no matter what the body is, it will be moving as a test body in some vacuum metric, and in a very particular vacuum metric. So if we go back to this picture, this local picture is still right, but this little patch we're looking at is not a little patch of the metric of the big black hole. It's a little patch that includes a correction due to the small body itself.
Adam, sorry.
Yeah.
When you say G plus H regular is a vacuum solution, you mean to lead in order?
To all orders that we know of. So there's a kind of a set of interrelated results here. So the results that I have proved is that second order in the small parameter, it's a vacuum solution, and the motion is geodesic in it, or a motion of a test body in it. But then there's complementary results proved by Abe Hart, which is actually for full nonlinear GR. It's specialized to a material body, so it doesn't apply to a black hole. But he showed essentially the same result in full GR, that there is a certain effective metric with certain properties that the motion is geodesic in. Now, his certain effective metric is not quite a vacuum metric, but he and I both believe there's a variant of it that is a vacuum metric. That still takes some work, but as you said, what we currently know is a perturbative statement that we know for sure, that through second order in your small parameter, epsilon squared, the motion is that of a test body in this metric, and the metric is a vacuum metric.
Sorry, could you comment on the relation with the effective one body approach?
So they are closely related in spirit, I think. The actual way the effective one body approach is built up is quite different. But the effective one-body approach, so there you take as an ansatz that in the two-body system, you can describe the dynamics of the two-body system as the dynamics of a test body in a deformed Kerr metric. So in that case, it's an ansatz rather than a result, but the ansatz was at the time based on the fact that this was true in post-Newtonian theory to all known orders. And then since then, we've got additional evidence from self-force theory. And then the particular way they build it up is quite different, because currently the way they build it up is either starting from post-Newtonian theory or starting from post-Minkowskian theory. Now, I think a very interesting avenue would be to actually start from self-force theory and build up your EOB that way.
Okay, thanks.
But yeah, spiritually, it sounds like they're the same thing. So they're very closely related. Okay, so what's the current status of these models? Okay, so to discuss the status, first I need to introduce some nomenclature. So we have this hierarchy of self-force models developed by Minderer and Flanagan. And the idea is on the timescale of an inspiral. So the timescale of an inspiral is 1 over the small mass ratio. So the smaller your mass ratio, the longer the inspiral lasts. On this long timescale, the phase of the gravitational wave has a particular form. So it starts off with a 1 over epsilon term because the phase accumulates roughly linearly with time. So the longer this thing is lasting, the more phase you accumulate. And then you have subleading corrections. And the thinking is, and we have pretty good evidence for this, that a model that gets this leading order term right should be enough to detect most signals. The requirements to detect most signals are actually fairly low. But then the requirements to extract information from the signals are very, very high. But a model that gets both of these terms correct should be enough for very precise parameter extraction, because really it's the waveform phase that is the key requirement in order to extract information from a waveform. And if your error is of order epsilon, and epsilon is 10 to the minus 5, what you're neglecting is extremely tiny. So this leading order thing is called adiabatic order. And for that, you need a very specific input, which is the dissipative piece of the first order self-force. So on long time scales, dissipative effects, which change the energy over time, those dominate on long time scales. Then this next term is called post-adiabatic order, or first post-adiabatic order. And that requires the full first order self-force, so including conservative effects that don't change the energy on long time scales. And the dissipative piece of the second order self-force. So we do need to go to second order, which is specifically why I was mentioning second order expansions earlier. Okay, what's the status of these models? Efficient methods of calculating adiabatic inspirals were developed actually quite a while ago, 15 years ago. And there's recent progress in actually implementing those and generating waveforms. So if you're interested in that, I'll point you to these recent references. This most recent one actually generated an adiabatic waveform from an inspiral into a Kerr black hole that was very similar to the one I showed in the movie early on. So there was an inclined orbit, it was highly eccentric, it was complicated. So they did that just as a proof of principle that they could generate adiabatic waveforms for generic orbits like that. Now, most effort over the last 25 years involving a community of anywhere between 20 and 70 people, it fluctuates with time. Most effort has been focused on calculating the full first order self-force, so the conservative, the dissipative, the whole thing. But it's essential to realize that this isn't actually an improvement over the adiabatic approximation if you don't also have this second order contribution. you could actually be making your model worse if you only include part of your post-adiabatic effects and not the rest of your post-adiabatic effects. So this has been my focus for the last 8 or 9 years, trying to calculate this dissipative piece of the second order cell force. Okay, so I'll show you some recent results in a moment. I'm realizing I'm way over time now. But I wanted now to connect this back to what I was describing at the beginning with this, this map of the binary parameter space. So there I said, there's different domains of validity for different methods. The method I've been describing is down here in the corner. Post-Newtonian theory, which is a much more developed method, is up here, and numerical relativity is down in the corner. Now, more recently, we have made this this cartoon into something a bit more quantitative. So this is work by Martin van de Bent and Harold Pfeiffer at the Albert Einstein Institute. So they've replaced the cartoon with this quantitative estimate of accuracy. So here's still numerical relativity down at the corner. Mass ratio is still going left to right in the same way. Orbital separations on the right up here, or you could equivalently look at orbital frequency here. But orbital frequency is going up as we go down. Okay, and post-Newtonian theory is still up here, but what you see is this first post-adiabatic approximation that comes from self-force theory, which is the small mass ratio approximation. That's actually covering most of the parameter space by itself. So in particular, it goes way into the numerical relativity regime and significantly into the post-Newtonian regime, although the post-Newtonian regime keeps going up forever and ever. Okay, so this was a quantitative prediction rather than a statement of fact. The idea here was they were taking numerical relativity simulations, a whole sequence of them over different mass ratios, and they were fitting the data to precisely an expansion like this. They're fitting the waveform phase to this expansion. And so they found that the leading term in that fit was precisely, to very high precision, equal to the adiabatic approximation that comes from self-force theory. And they found once they added the next term, again, just looking at a fit, you get this remarkable accuracy over most of the domain. So once you go way down here, then you will have to resort to something else, numerical relativity. But this is pretty surprising, at least if you don't know anything about this, it's pretty surprising that this approximation that's designed for having one object much, much smaller than the other is actually surprisingly accurate over here, where the mass ratio is actually 1-to-1. These are equal mass objects. Now, more recently, this work I've been doing with collaborators at University College Dublin and my former PhD student, Jeremy Miller, we have more quantitative evidence of that statement. So this is results of a simulation of a quasi-circular binary around a non-spinning black hole. So we just take a Schwarzschild black hole and we set a little body going around in a circular in spiral around it. And we calculate the energy flux emitted in gravitational waves. So on the vertical axis, we have the energy flux divided by the leading post-Newtonian energy flux. This is for mass ratio 1-to-10. The blue jiggly curve here is from numerical relativity. The x-axis is essentially frequency. And the idea is, as the in-spiral proceeds, you go from left to right. So this is, on the left is very far from the black hole. On the right, here we've plotted the innermost stable circular orbit around the black hole. This yellow curve is 3.5 post-Newtonian order. So this is a post-Newtonian approximation that's almost as accurate as is currently available. Actually, for this, it's the most accurate, I think, that's currently available in the literature. the green curve is what you get with the leading self-force theory. So you only go to order epsilon in the mass ratio, not epsilon squared. And then the red is if you include the subleading correction. So you're going to second order in the mass ratio. And you see you get pretty amazing agreement. So even first order self-force results, it's only about a 1% difference here between numerical relativity and self-force. But then once you go to second order, it's really incredibly accurate over a wide range. It does get less and less accurate as you approach the end, but this is actually within about 1% the entire way. Now you might think, okay, well, that's mass ratio 1 to 10. That's a somewhat small number. Here's mass ratio 1 to 1. So two equal-sized objects. And again, you see pretty spectacular agreement between second order self-force calculation and full numerical relativity. In this case, you see a much bigger disagreement between the first order self-force result and numerical relativity. And we can go a step further. These are for non-spinning binaries, but we can add spin to the companion that's going around. And again, we see amazing agreement. So this seems to suggest that the Einstein field equations are maybe not as nonlinear as we thought. A perturbative treatment actually seems to converge pretty rapidly over a big chunk of the parameter space. Obviously, though, it depends on what your expansion is, because you see post-Newtonian theory zips off in the wrong direction pretty quick. So that the post-Newtonian series is not converging nearly as rapidly as this expansion in the mass ratio. Okay, now just to summarize, what is the current state of the field? The ultimate goal is to have second order self-force simulations of inspirals that are generic, so they're inclined or they're eccentric, into Kerr black holes. And we can kind of build up adiabatic information, first order, second order information. In 2005, 15, 16 years ago, all we had was adiabatic orbits in Schwarzschild or circular in Kerr. A few years ago, in 2017, Martin van der Ment had calculated the first order self-force on a generic orbit in Kerr, not driving an inspiral. That took a few years more, but now there has been at least an inspiral at adiabatic order for generic orbits, and we do have access to first order self-force data for generic orbits. And now we're first putting the stamp onto second order calculations. And now we need to race down here to the bottom within the next 10 years in order to have this all ready before LISA launches. Okay, so to summarize.
Can I ask just a quick question?
Yes.
What is the expected precision? So you can tell the difference in precision between the 2% of the first order self-force and the nearly perfect agreement with the second order. But can LISA do that? I may have missed that.
So it's important to realize that what we're comparing against here is numerical relativity used for comparable mass binaries. So this actually isn't what we're aiming to use this approximation for LISA. We really do want it to be an extreme mass ratio inspiral with a mass ratio of 10 to the minus 5. And there we don't have anything to compare against. What we will provide will be the most accurate estimate.
I see.
But this is really the basis of our estimate of what we need to give. So we know that the second order effects that we're calculating contribute to this term here, which is an order 1 term. So it'll be, well, based on this estimate, it'll be maybe 10 radians over an inspiral. And we need to be accurate to much less than 1 radian error over all 10 to the 5 orbits. So if we're out of
I
phase
see.
by a few radians, the game is lost. We can't get anything.
Okay. All right, thanks.
Now, the worst case scenario would be that this next term that we're excluding is also important. Then we'd be in deep, deep trouble.
Actually, Adam, can I ask something about this? Because
Yeah.
the statement you have here at the end, the last bullet, I mean, this is going to be signal to noise ratio dependent, right?
Yes.
So when you say that the phi1 is enough, you mean at the SNR of 10, 100, or 1000?
So we certainly don't expect EMRI signals to have SNR of 1000. This is enough so that the model won't be the limiting factor, but the SNR will be the limiting factor. So we're really focused on EMRIs that will have SNRs of 50 or 100 or 150, which are loud. This is integrated signal to noise. So you build it up over the course of the inspiral. And yeah, the idea is we need our model to be precise enough so that we can actually get the information from that signal. So the model is no longer the limiting factor. This is a problem actually in gravitational wave astronomy in general, that there's a very high risk that once we have next generation detectors, the modeling systematics are going to be dominating over the experimental noise. So there's a race against time, not just for EMRIs, but also for every kind of signal. So for example, the supermassive black hole binary in spirals, where you have 2 massive black holes colliding, they're so loud that they're going to dominate over everything else. And so you need your model of those things to be incredibly precise, so that once you have basically removed them from the signal using your modeling, you're able to extract what's underneath. Otherwise, your extraction of the signals that are underneath might get totally ruined by whatever residuals you have left, because there's just so much in that signal. So yeah, it's a race to keep up with the technology development.
But just to be clear, I'm a little confused. So the GR prediction that you get from your cell force models for this phase phi of the gravitational wave, is it some simple functional form with a small number of parameters that you try to fit to the data? Or is it that you just scan parameter space and you get a bunch of templates?
Okay, so the data analysis methodology is going to be totally different than what's done with LIGO. So with LIGO, it's exactly what you say. You generate a big bank of templates and you just go in and search. You just look. Does your data match this? Does it match that? Does it match this? You just go on and look. That's not going to be feasible with EMRI signals, because the estimate is that if you wanted that kind of search method where you build up your entire template bank first and then you search through it,
the parameter space is too big, right?
It's way too big. Yeah, you would need, the estimate is you need 10 to the 40 templates, which is obviously not going to happen. So instead, the idea is to use, what is it called? What is it called? Like a Monte Carlo based method where you're kind of jumping around the parameter space a lot, and you kind of use more and more act waveforms as you narrow in on the region containing your signal. So
yeah, that's what Salvo put in the chat right now, by the way.
Actually, can I see the chat?
Yeah, I can comment so you don't have to leave a full screen. I was just saying, Adam, that even for LIGO, the template bank is only used for searching, but for parameter estimation, we do not use a fixed template bank. We use a stochastic sampling based on NCNC, and depending on the problem you are dealing with, maybe fixed dimensional, can be transdimensional or whatever else. But I would just want to, I know that's a common confusion in LIGO data analysis. We do not assume that templates live on a grid when we estimate the parameter. That's just the first pass to find the thing. Then we do
Right.
something more sophisticated.
So the big change is that even for search, that's not going to work for EMRIs.
I appreciate that. Yeah.
Yeah. But yeah, thanks for that clarification.
Okay,
Okay.
so yeah, the MCMC thing makes sense. You narrow in on parameter space and then you find a better and better fit. But if that doesn't work, so is there a functional form for phi with a small number of parameters, or what do you do instead?
I don't think there will be a nice simple form for it.
Wait, so let's take phi naught. Let's take the simplest one, phi naught. So what is, I mean, you say people, you put check marks, people computed phi naught. So it's a formula that depends on some number of parameters, or what is it?
No. They have not computed phi naught like that. They've computed numerical simulations of, they've calculated that numerically. So they do not have a simple formula for it. I wonder if I can.
Well, do you see why I'm confused? Because if I just randomly draw a waveform and I ask you, is that compatible with GR and the curve prediction? You have to tell me if the answer is yes or no. And how do you give me that answer? Do you just go searching through parameter space until you find something that fits? How do you know when you've searched long enough? Can you always find something that will fit? What's the logic?
Because the signals are so distinct. I wonder if I can show you an actual waveform. How do I get out of this full screen? Okay, let's see if I can find an actual waveform. Yeah, so it's very hard to fit something like this. With just a made-up model. This is actually not as complicated as they get. This is a fairly weak field signal. So the hope is that because they're so distinct, you won't have so much degeneracy.
So parameter space has two parameters, which is the initial separation and the mass ratio. And for each...
No. Parameter space is big. So you've got the mass ratio, you've got the spin of the small object, which has several degrees of freedom. You have the eccentricity, you have the inclination, you have the semi-major axis, you have the spin of the big black hole. There's a lot.
Right, so very naive question. If I have a very complicated parameter space with many parameters, how do I know that I can't always fit something? I don't know. I mean, I have no idea what that parameter space looks like, but a priori, I mean, maybe I don't know how hard it is to find something in there that looks like this or not.
So if you take a little patch, it's not that hard. You can just throw in some sinusoids with, as long as they have the Kerr frequencies, the frequencies of Kerr geodesics, you can reasonably well fit a small patch. But the longer and longer your waveform goes, the harder and harder that gets. So part of the idea. Go ahead.
So you're saying in practice, it's just really hard to even find one position parameter space that reproduces this whole curve.
Oh yeah, it's much easier to miss these things than it is to think they're there when they're not.
Well, okay, but that's reassuring at least for the experiment.
But I should say, I mean, I'm not a data analysis guy. I'm a I'm a very much a theorist modeling guy.
Right, we're running a little over time, so maybe Adam, you want to go back to your main talk and
Sure, yeah.
finish up, and then we'll have two people who've been patiently raising their hand for questions.
All right, how do I get back to where were we? Here we are. There we go. Okay, I don't think I went over the conclusions, but I'll just leave them up there. If you want more information, there's a very technical recent review that I wrote with Barry Wardell, and there's a review for non-experts that I wrote with Leo Brack a couple of years ago.
Okay, yes, thank you. Thanks, Adam. That was very nice, very informative. So Angelo has the first question.
Hi. So if I heard you correctly, you're talking about 5 sig figs and mass and spin. In there, are you sensitive to the distribution of other matter, the other stars and gas in the vicinity? And if so, what are you going to do about that?
That is a very important question. So partly it depends on which galactic core we're looking at. So the estimate is that for most galactic cores, the effect of an accretion disk, for example, is not significant enough for us to see. Basically, because it's a fairly weak effect compared to the big black hole, and the EMRI is so close to the big black hole. For active galactic, for AGNs, there the estimate is that environmental effects will be comparable to the first post-adiabatic effects. And I think that means we're just not going to be able to model those.
Okay.
There's also the possibility of having effects due to, say, a third body that's relatively close. It won't have like a big continuous effect, but it can create a resonance if its orbit, becomes resonant with the main body you're interested in, and that can have an observable effect. Now, the good thing about resonances are that they create a very unique signature, so that's something we might be able to actually, something we should be able to actually model and actually see if that happened.
Thanks.
Alfredo?
Hey, yeah, just a follow-up comment. Maybe because the discussion has been centered on extreme mass ratio spirals, but I'm sure you know that it has recently been noticed in the context of the post-Minkowskian theory, right? So we can apply these self-force results to actually comparable mass ratio Hamiltonians, right? So if you write down, let's say, an effective Hamiltonian for arbitrary masses, the dependence on the mass is very constrained in such that actually you only need to determine the first self-force coefficients. So actually, it might be that even though your results are suitable for LISA and extreme mass ratio in spirals, it can also be that they also have to say something about the comparable mass ratio situation. So that's true for the post-Minkowskian, but I'm thinking maybe also in the cases where the distance is shorter.
Yeah, so in post-Minkowskian theory, you do have that really nice effect where if you go one order higher in mass ratio, you get two orders in Postman-Minkowski theory. So yeah, I think if we had second order self-force calculations for scattering orbits, say, yeah, then I think we'd be able to fix sixth order Postman-Minkowski in theory. So yeah, so this
Yes.
has been a big part of the self-force program. So here I was focusing on just directly comparing self-force to numerical relativity. But it's not like this would actually be accurate enough for next generation detectors to use this directly for comparable mass binaries. But yeah, a big part of the program has been using self-force data to inform post-Newtonian theory and inform effective one-body theory.
Yes, I'm just talking at the level of the Hamiltonian, right?
Yeah.
So we suspect that. So it doesn't matter if it's extreme mass ratio or comparable mass ratio. The Hamiltonian is the same, and therefore you can inform it in the extreme mass ratio limit, and use those results for the comparable case.
Yeah, exactly. Yeah.
So would this tell you something about, let's say, your phase shift? Can you compute this phase shift as well for comparable mass ratio? There is no.
Yeah, definitely. Yeah. So I would expect within a few months, well, it's probably overly ambitious, but hopefully by the end of the year, we will have actually simulated quasi-circular inspirals and actually calculated this phase shift. And these coefficients we're calculating are mass ratio independent. So
I see.
We don't need to specify the mass ratio when we calculate them. We only then, the time scale hidden inside here and this overall scaling, that's when we put in the mass ratio. But yeah, we first calculate something that's mass ratio independent. And yeah, then we can, in principle, apply it for any mass ratio.
But do you do a post-Newtonian expansion at the same time?
No. We never do any post-Newtonian expansion.
Okay, so it's pure self-force.
Yeah.
Okay. And how do you know that? Sorry, yes, last point. How do you know that these are mass ratio independent if you're using self-force to compute them?
They are by construction. So this form comes from self-force theory with mass ratio independent coefficients.
I see. So it's in the derivation of the self-force.
Yeah.
I see.
All right. Last question, Salvo.
Yeah, I'll be quick. Thank you, Achilles. So Adam, I was wondering if the paper of a few days ago by Letiec about proving basically that Kerr black holes do have a non-zero tidal deformability, so a non-zero log number, does change your approach at all, or is not built anywhere that the black holes that you're dealing with are perfectly rigid?
Yeah, so I've always been a little bit confused by Alex's take on this. I don't know if you're aware of the arguments he's had with other people about whether this is a uniquely defined love number. But from the perspective of the kinds of models that I'm working on, it doesn't actually matter. We're just solving the Einstein equation, and whatever the solution is, that's the solution. So if the black hole does develop a quadrupolar response, that will already be in our solution.
I see. So it's not built in that it doesn't.
Exactly. No, yeah, we don't.
Okay, thank you. That's what I wanted to understand. Thanks.
Yes, very good. Thank you, Adam, for a very nice, stimulating talk. It was very good overview for us. Lots of questions. Great. We'll see everybody next week.
Right. Thanks a lot. That was a lot of good questions.
Thank you.